Hey guys, so this is my video submission for lab 2, motion of a falling object. So in this lab, we observe the motion of an object that's dropped from rest and falls slowly. Then we extracted the position data of that from Tracker. Then we constructed two computational models. Um, our computational models were related to drag and gravity. So one had the effect of drag and gravity, and one was just gravity. The fundamental physical principles in this lab were like Newton's second law. You could say the momentum principle. We talked about terminal velocity, drag force, the formula for drag force, and really how terminal velocity works, which we're going to get to in the final questions. Um, I'm also going to be showing you guys some figures, and I can now show you guys my video. So my video was me dropping a volleyball in my dorm. The system is the ball, and the surroundings are just everything around it, like gravity is acting on the ball.
Yeah.
So then I was able to take the frame from when I dropped the ball to when the ball fell on the ground and extract that data into Tracker. Then I created my two computational models, figuring out how to write the drag equation in GlowScript. So these are my position versus time graphs. As you can see, green represents gravity only, blue represents gravity plus drag, and red represents the experimental data. And I was able to do this all on GlowScript as opposed to another spreadsheet model. So next, we were asked to compare my models to my observations by plotting everything on the same graph, which I just showed you guys. And now we're going to answer some of the what does it mean questions. So what does it mean asks is that examine the velocity versus time predicted by your models with and without drag. Which models, if any, predict a terminal velocity? So terminal velocity is basically the in physics concepts, it would be that there's a net force of 0 because the air resistance is actually canceling out the force of gravity, which creates a constant velocity. So I'm going to show you guys my position versus time graph and explain which one demonstrates the concept of terminal velocity. So here we have the experimental data and we have the gravity plus drag. Notice that the gravity plus drag over time, the slope of the line um doesn't become the slope of the line becomes constant. So the change in the slope becomes constant. So as you can see, we have a constant velocity because if we took the derivative of the gravity plus drag here, it would be changing over time, but eventually it approaches a constant. Uh, so to me, the gravity plus drag best represents the concept of a terminal velocity, and it also makes sense in physics principles because of the net force of 0 concept that I described earlier. Now we're going to look at the what if. So it says, imagine that the object was initially thrown downward. Would the terminal velocity in this case be the same or different from the case where the object was initially dropped from rest? So if the object was thrown rather than dropped, the initial velocity would already be high, so it'd actually take less time for the terminal velocity to reach because it just needs to decrease. So I actually created a computational model to explain this. So here, if notice how over time the velocity becomes constant in the gravity plus drag because of the terminal velocity, this would take a lot less time because the velocity is already at a value as opposed to 0. So getting it to a terminal velocity would take less time. Uh, that's basically the entirety of my lab report. Um, I just wanted to establish some other things. So possible sources of error could be the fact that the actual video didn't occurred in a very small time interval. Uh, I don't think there are any other possible errors, and the initial conditions uh was just the ball dropping. Everything else is computational. I think that's the entirety of my lab report. Thank you guys.